Welcome to Lesson 9, an introduction to the computer program EPANET. In this introduction, we're going to present you with EPANET. There's a separate video that goes through the installations on a PC or installations on a Macintosh. On the Macintosh, the methodology is entirely experimental and unsupported. So on the chance it doesn't work for you, you'll have to make alternate arrangements to be able to find a PC. Those arrangements could include something like Parallels in a Windows operating system, or VMware in a Windows operating system, or Boot Camp in a Windows operating system, or just buy a cheap Windows machine. Those all cost about the same. Then we'll take a little background on the program, perform an interface tour, and then we have some example problems. So just refreshing our memory, here's the system components. All the components depicted in this figure are more or less replicable in the EPANET modeling software. The modeling software represents a distribution network, and it's comprised of items that are intended to convey potable water at adequate pressures and discharges: tanks, pumps, pipes, valves, other fittings, meters, and other appurtenances. So EPANET itself is a computer program that simulates flow in closed conduit pressurized systems. Functionally, it's identical. The computation engine works identically to the Newton-Raphson hybrid method that was presented in the earlier in the course. Naturally, it's not running in a spreadsheet anymore, but the underlying arithmetic is essentially the same. At nodes, we're going to specify elevations and demands, and the computer program, once it's assembled, calculates the resulting pressures. In links, those are things like pipes, pumps, and valves, so we specify their behavior, frictional loss terms, settings, and whatnot. And then there's a special type of node, which is a reservoir node or a tank node. Reservoir nodes are also known as fixed grade nodes, so we supply a value of total head, or think total pool elevation, and it's maintained constantly in the simulation. It doesn't change, and hence it can represent a large supply of water. Tanks, on the other hand, as we discussed earlier in the class, have water pool elevations that change with flow coming into or leaving the tank, and those are accommodated appropriately. There's a demand schedule, so when we're dealing with tanks that are going to drain and fill, we're no longer doing single steady flow runs. We're going to do a sequence of steady states, usually on an hourly time scale, and the program will compute the water level at the beginning of the time period, at the end of the time period in the tank, and in some other features, and that's conveyed to the program through something called a demand schedule. To get a copy of the program, you could Google EPANET if you're a PC user and get to the EPA website and download it there, or you can use the class website, which has a link to the same place. For Mac users, you're pretty much limited to the class website. The application bundles that I provide in the class website are essentially similar to those that are available elsewhere. So if for some reason you don't want to get it from a Texas Tech professor, that's fine. EPANET.de is a German website that also has Macintosh application bundles available. You also are going to want to get a copy of the user manual, either from the EPANET website or the class website. It's kind of important because it explains how the program works. Contains, I would say, sufficient tutorial to get up and running with the program, as well as some advanced features. If you actually want to run the program from an input file and edit the input file directly, it explains how that's laid out. The program we're using, we construct the network topology in a graphical user interface. So unlike what we were doing in the by hand examples, we still need to draw a picture of the network, but we don't necessarily have to construct the +1s and -1 coefficients to get things in the right place in the matrix. The computer program manages that activity on our behalf. We have to provide lengths, diameters, friction terms for each component, pipes, valves, and so forth. If one of the components a pump, we also have to provide a pump curve. And then demand is entered at each node. We use a positive value if the water is leaving the node to supply a customer, and occasionally we'll use negative values to indicate injection into the network where a problem requires that kind of structure. Doing negative demands is, I'd say, less common than the usual convention of positive demands. More about the program. So the nodes have demands at each node, and we need to supply an elevation for each node. The default elevation is 0, so if we don't supply an elevation, it's going to assume that all pressure calculations are referenced to Z equals 0. The lengths, if they're pipes, we're going to provide length, diameters, friction terms. Pumps and valves are also treated as link components. They have different data entry requirements. And then a reservoir or a tank, all models need a reservoir or tank. It performs the same role in a hydraulic circuit that the ground does in an electric circuit. Things you have to choose. You have to decide what head loss model you want it to use. Darcy Weisbach, Hazen Williams, or Chesey Manning. You have to choose flow units, cubic feet per second, gallons per minute, cubic meters per second, and so forth. By selecting flow units, you're implicitly selecting SI or US customary unit system. The program does not convert unit systems. So if you enter all your data in US customary and realize that you had meant to do an SI version and you switch to an SI flow unit, it'll handle that just fine. The numbers that you've entered won't change. And so if the units are not directly transferable in that fashion, you would have to go back and individually change each of the pipeline links and so forth to be consistent with the new unit system. So here's what I suggest as a modeling protocol. Sketch a layout on the paper. On that paper, identify pipe diameters, length, roughness values. You should name the pipes. Identify node elevations and demands. Identify a supply reservoir. Identify the reservoir pool elevation, and identify any pumps and pump curves in the problem units. Then start EPANET and build the model. So we're going to go through a couple of examples to first get familiar with the modeling tool, or get familiar with the program, and slowly develop the skills needed to use it for far more advanced problems than are shown here. So our first example is going to be this one. Flow between two reservoirs. We've done it as homework earlier in the course, and we'll simply repeat it using EPANET. And then the second one will be the same example we used to motivate the Newton-Raphson solver conditions, as shown here. And that will be the two examples. But first, we'll get the software installed. So the videos to download the software are located in this same lesson, lesson 9. The first one goes through how to download and install on a Windows machine.
Hello and welcome to part of lesson 8, which is installing EPANET on a Windows 10 computer. And what I'll go through now would also work equally well for Windows 7. In the software section, EPANET for Mac is provided. But to do EPANET on a Windows machine, the options are to Google the EPANET website. Simply just do EPANET, and it will take us to the epanet.gov download page. expand the software documentation and downloads link. And you're going to want the self-extracting installation program. You probably don't need the toolkit files unless you're going to do some advanced coding. Multi-species and real-time extension are also some advanced things. If you want the source code and you're going to compile from source, it's right here, and you'll probably want the user manual. I'll also show you another place to get the information from. So if we choose self-extracting archive, I'm going to save it. Hopefully that saved it. Spinny beach ball. View my downloads, and I now have a download EPANET to setup.exe. I'll go ahead and run that. Ooh, download is unsaved. Interesting. Try that again. All this safety, it doesn't work. Save target as. Local disk C. Download is complete. I'll now try to run it from the download directory. Local disk C. Users. Theodore. Downloads. EPANET 2. And attempt to run. Go ahead and choose yes. I suggest you accept the defaults. If you're running on a university machine, you can't actually install to a university machine. You'll be forced to use the default. You'll be forced to change this to an external drive. If it's your personal machine, EPANET 2 is quite safe. And it's now complete. We finish the setup, and we now have the EPANET 2 interface. If you get the interface, you're pretty much assured that the program will be running correctly. If you want to check it, a real quick and easy model to build is a reservoir node. Connect them with a link. Set the reservoir head to something meaningful. Set the demand to something meaningful. Pretty sure the defaults will handle the rest. Run was successful. That concludes how to install EPANET on Windows. The usual location of EPANET is in physical location should be, it's in C, program files x86, EPANET 2, and this one is the legacy EPANET, and the one I just installed is in 2.0.12. Looks like the help files have been updated. These might actually run now. Cool. Alright, well that completes the EPANET 2 installation.
So that's how to install it on a Windows machine. And here's the same game done
This
on
video
Macintosh.
illustrates how to download and run EPANET on a Macintosh computer. The software application bundle for Macintosh is located at theodore-macbookpro.ttu.edu. Go into that website, take the software link down here, choose EPANET Mac OS, choose EPANET Online, and we're presented with a directory. It has a README instruction, a little bit about the application bundle, and what we're after is this file, epanetonline.tar. We're going to right click, download the linked file, and we'll let the download begin. And again, depending on the speed of your network, that download can take anywhere from minutes to several hours. In this case, it's going to take about 5 minutes, so I'm going to pause the video while the download completes. Okay, so the application bundle has arrived, download's complete, and it will be located in my downloads directory, epanet1.tar. Move it to the desktop, create a directory for it to live in. I think it's in the best interest of the user to keep it separate from the other programs you install and you put into the applications directory, namely because this bundling is not necessarily done by a signed developer, and I don't think you want to mix the two. To extract the application bundle, we double click on the tape archive, let it extract. And to do the first run, we'll double click on the application. And it issues this security message which says it can't be opened because the identity of the developer cannot be confirmed. What we'll do here is we'll override this security in the preferences. And it's a one-time override. Once it's installed and running, you don't have to do this again. So we go to System Preferences, Security and Privacy, and it says EPANET Wine was blocked. Choose Open Anyway. Now we'll go ahead and open it, and it states here opening will always allow it to run on this Mac. And we have a successful installation. We can test it by making a very simple network. Put a supply here, 40. Run it. Choose OK. Sure enough, there's some flow in that pipe. And we could even go so far as to have it draw pretty pictures for us. Okay, we have a successful running EPANET model, and that's how you would download and install an application bundle to run EPANET on a Macintosh computer.
Interesting. Didn't know the last minute of the video was blank, but that's okay. So that handles the installs. So let's now go take a tour of the interface. I'll do that by starting my copy of EPANET. And here we have the interface. Usually it will come up with this drawing canvas area called the network map. There's this browser dialog box that normally positions itself to the right. Just by way of warning, they can get covered up so the browser can get lost. You want to avoid closing the browser because reopening it is some menu item and you don't do it enough to remember how, so you can take quite a bit of searching. It's easier just to not close it. We have menu items up here, so File, Edit, View, Project, Report, Window, and Help. The help topics don't necessarily work on Windows. It looks like that's good. Yeah, that's what I was expecting. The help item doesn't work in the application bundle. Actually, it doesn't work well in Windows 10 either. If you have an old Windows XP machine, it'll work great. And I think Windows 7, the help item works. Everything that's in the help is also in the user manual. We have hydraulic components up here that I am now moving over. So a junction, reservoir, tank, pipe, pump, valve, and then you can, the T is a text box, so you actually can type text directly on the network map. We have a region select, it's a polygon, and panning, zooming in and zooming out, and then full extent returns everything back to the full size. And then you have the select object icon and a few other items here. This little lightning bolt will run it, and you can also run from the project menu item. So continuing the tour of the interface, I'm going to make the drawing map small, and we'll do a very simple example. We'll just have a reservoir, a node, and a link. At the reservoir, we'll specify a non-zero value of total head. I seem to like 100, so I'll do that. At the node, we'll specify a non-zero value of demand, 2. Leave everything else as defaults. So currently, the project defaults are gallons per minute, Hayes and Williams head loss formula. And if we go look at the default pipe, it's a 1,000 foot, 12-inch diameter, Hayes and Williams coefficient of 100. Run it. The run was successful. We can look at the pipe, and it says we have 2 gallons per minute flowing through the pipe. It's not going very fast. The computed friction factor is 0.076. We can turn on the map over in the browser. We can turn on values for demand, and let's go ahead and put flow, and it will use colors to represent different ranges. In the view menu, we can go to options, turn on the notation, and we'll have it display the node values and the link values. So -2 units of demand at this reservoir because it's going into the network, 2 units of demand at this junction because it's coming out, and 2 units of flow in the system. If we change from demand to pressure, for instance, the value is computed on our behalf. So there's 43 psi in this system. So that's the quick tour of the interface. The other important part is in the file menu. We can export the network to let's call this, what do we call this? Interface tour. And let's see, it was in KRAPP, I think. There I went, interface tour.inp, And that file is actually an ASCII text file. So I'm going to open it with a text editor. And that is what the input file for that particular problem looks like. Not substantially different than our spreadsheet, although there's some more information down here in controlling various parts of the simulation. Has all the options and the information that allows the drawing to occur. So that completes the interface tour. Okay, the next thing we want to do we're going to want to do is this particular problem. So I have EPANET already running. Remember how to get it to come back to life. Sometimes in the Macintosh one, there we go. Oh, didn't expect that to happen. Sometimes we have to quit and restart. It's just the way it is. Save changes in current project. No. So I'll go restart my EPANET. And what I don't want to do is minimize it, but I want it small enough to work with. Okay, so I'm going to grab this whole picture. Grab, capture, selection. And I want to save that as a bitmap. See if I actually have that as an option. I do not. So in my case, I will put it here, and then I will now save that as a bitmap file. Save as. BMP, and let me put it on my desktop, in my Playhouse, and actually I'll leave it there on the top. Alright, now there was a reason for doing that, and we're about to see the reason. Okay, let me get my EPANET back. So the advantage of, remember in the protocol you want to draw out your system and label things? Okay, here's why. You can draw it out, you can take an image of that drawing, save it as a bitmap, and I now can load it in to my project, and I have a drawing. And I can then operate on the drawing. So in this case, we're going to put a node here and here. We'll connect those two nodes with the 2-mile long pipeline. We'll put a reservoir here and here. Now I'm going to connect these reservoirs to those nodes with what will ultimately be short pipes. So I'm going to make them short and large diameter so they have no head loss. And this is a modeling trick. EPANET will not allow us to draw a pipe between two reservoirs. There has to be at least one node, and I find it easier to just put two nodes. So this junction needs to have an elevation. Let's just arbitrarily put it at 100. We'll put this junction at 80. I will arbitrarily put this reservoir at 110, this reservoir at 90, so both reservoirs have 10 feet of fill depth above their respective junctions. This little pipe, I'll make it pretty short, fairly large diameter, and let's see, this is iron, so we're going to need to switch flow systems in a second. 0. I think that'll be a decent value for iron. So that's 0.011 millifeet of roughness. Once I switch to Darcy-Weisbach, we'll do the same here. Okay, so these little pipes, very short, large diameter, aren't going to have, they're going to have negligible head loss. So whatever the head of this is immediately transferred to that node. This pipe is 24 inches for the 2 foot in diameter. It is 5,208, 10,560 feet long. We'll use the same roughness. And everything's ready except for getting the flow units. Let's put it in cubic feet per second, and let's use Darcy-Weisbach. Choose OK, and we should be ready to run our program. We can remove the backdrop and see the picture. Run it. My run was successful, and as I recall, we run the online tool with about the same settings. We get around 11 cubic feet a second in the pipe. In this case, we get 14. So let's go ahead and find that out right now, since we have another way of this particular problem. In our toolbox, we have an online calculator that does flow between 2 reservoirs, no pumps. Pretty much the same problem. So pool elevation 110, number 2 was 90. We'll put all of our minor loss coefficients at 0. Pipeline length was 10560. Pipeline diameter in feet was 2. Sand roughness height was 0.123011. Kinematic viscosity 1.1 E minus 5. 32.2. So obviously all that's done internally in EPANET. Run it, and we amazingly get the same answer. Some of these ones, so our computed friction factor is 0.0121, EPANET's is 0.012. So we essentially have done the same thing as a homework assignment a long time ago in EPANET. So that's example number 1. Let's look at example number 2. Now we probably just want to grab the 3 pipes, but we do need to remember that everything's 850 millimeters long. I'm pretty sure I have this drawing already on my desktop. So I'm going to just do a new project. Oh, it's a PNG, isn't it? I'll go ahead and I'll have to do that capture and select thing again, unless I can find it on the desktop. You go away. Open with, do a quick conversion. Okay, now it's a bitmap. Load in the backdrop. There's my setup. We will do the reservoirs A, B, C, have junction J. We'll connect the reservoirs. If we really want to adhere to the curviness, we can, or we can just do them as straight lines. We need to supply the pipe lengths. So 900 meters, 850 millimeters, 0.085. I forget what the correct number is from the prior example. 800 meters, 850 millimeters, 0.085. 700 meters, 850 millimeters, 0.085. So the pipes are now all set. We need the reservoir. A is 100, B is 80, C is 60. We can call that C, B, A. Call this node J because we're not terribly creative, and we have to decide what elevation J is at. We'll leave it at 0 for now. That can be changed on problem-specific basis. One last thing, we want to get the problem defaults in the correct units. So this one, the closest we're going to have is liters per second. Wait, is there cubic meters? No, just cubic meters per liters per second, and 1,000 of those is 1 cubic meter a second. And earlier in the class we used Darcy-Weisbach. Run it, and let's go ahead and map at the nodes. We'll map heads, and at the links we will map flow. We will turn everything on so we can see it. Notation, big enough to see. So the nodes are labeled A, B, and C. The junction is J, and then the numbers next to the nodes are the heads, 100, 80, and 60. Admittedly, yellow is hard to see. The junction J has a head of 79.70. If we decide that we want to be able to see that, we can change the colors that it's representing. And then pipes 1, 2, and 3 are shown. So that concludes example number 2. And that concludes the first of the 2 lessons on Introduction to EPANET.